Class. Okay. So we can talk about energy transfer in a circuit. So I drew a very simple circuit here where we have a power supply. You can think of a battery with a battery at a particular potential. It would be like a 12-volt battery or something. And we have wires going into some box. Like say you don't know what's inside the box. So you can just see a current coming in and a current coming out. And let's kind of trace what, like a small charge as it goes around the circuit. Now, overall, energy is going to be conserved here. So this charge is not going to gain energy if it completes a circuit. So we have an amount of charge dq, and let's just follow it. When it goes across the battery, it is going to gain energy. And basic equation, the change in potential energy is equal to the charge times the change in potential. And so it gains an amount of energy, dq times v, going through the battery. So let's say it has very low energy here. Now it's energetic. That's what the battery does. It's giving energy to this charge. And when it goes into this device, it has to lose all of that energy because it's going to end up back, back where it started. Now you might wonder, what if we don't put a device there? So, we're connecting the battery and this device with wires, and technically wires have to be a factor. However, the resistance of a typical wire, like if you're just have a copper wire connecting two things, typically that is extremely low. So we can disregard the interaction, like what's happening to the charge as it flows through the wire, because the resistance is so low. Now, if you replace this box and just have a wire going through there, well, then that energy has to go somewhere, and in that case, the overall resistance of our circuit would be extremely low, and that means we'd have a very large current, and so that can dissipate energy in the resistors. But let's say that there's an actual device inside that box. So basically, if we have like a 12-volt battery, there's a 12-volt potential difference between one end of the box and the other. And again, that's actually fairly realistic because the energy lost is going to be, tiny compared, or like the potential difference between one end of the wire and the next is going to be extremely difficult to even measure. So, this charge gains an amount of energy, dq times v, from the battery, and so there's nothing else, nowhere else to lose that energy. It's all going to be in this device. So the amount of energy dissipated by the device is just going to be dq times v. And let's look at the rate that energy is being dissipated. Now, let's also write down our definition of current. I is dq dt, so we can write this as I dt times v. Now if let's see if there's any mathematicians around. No, we're good. Let's divide by dt. The rate that energy is being dissipated by this device is I times v, the current times the voltage. And this is a general result. Current times voltage. Now this is a very important result because one of the main reasons we study electricity is it's extremely useful. We use electricity to deliver energy. And so P is the rate that energy is being delivered. That is current times voltage. Now this is a very general result. So that energy is being dissipated somewhere in this box. What is actually happening to that energy? It depends what's in the box. Now, if we have a resistor, what's most likely happening, well, what's definitely happening is this energy is being converted into heat. We've seen that. We talked about that, the electric field is doing work on the electrons, but overall they're not gaining or losing energy. So when they're colliding with the atoms, they're giving that energy to the atoms in the form of heat. Now I say generally that's where the energy is going to go. If you heat up a resistor enough, it can actually glow, and some of that energy can be released in the form of radiation. You can see this if you have a toaster. Just push it down, you can see those coils glowing red. Yeah, that's the electrical energy heating up the wires enough so that they're emitting radiation. So some of that power that you're supplying with the battery is going into radiant energy. Mostly it's going into heat. So that's if there's a resistor inside. There could be a light bulb where almost all the energy is going, well, it would generate some heat as well. But if you have a light here, a source of light, could be like an incandescent light bulb or an LED, then that energy would maybe mostly be going into the form of electromagnetic radiation. This device could be a computer. So maybe it doesn't even have a monitor, but the computer could be doing calculations. There's a lot going on inside a computer that's using energy. You could have an electric motor, which is turning this into mechanical energy. So, a very general result. Power is current times voltage. Now, a special case, though, is if we have a resistor. So we can write this in two other ways for a resistor by combining with Ohm's law. Let's write that up here. V is equal to IR. So we can have power is I times IR. So we can have power as I squared R. Or we could do this. We could have the current is V over R. So we have V over R times V. So we could also have power is V squared over R. And again, those two results only apply to resistors. Now, on your equation sheet, you're going to have this. You're not going to have these two because you don't need them. That'd just be kind of wasting space on the equation sheet because it's very easy to combine these two to get those results. So let's do one quick problem and kind of leave it at that. Let me read the problem. Just pick kind of a random problem from the book. It says, a steel trolley car rail has a cross-section area of 56 centimeters squared. So a lot of times when we're talking about conductors, they have very low resistance. So remember the resistance, the resistivity of a metal is very small number. However, if you have a large length, you could wind up with a significant amount of energy lost. It's basically, you want to deliver energy from one place to another. This result here, or if we're looking at resistors, that energy is just being lost. So it's being converted into heat, which isn't really useful. So here we have this cross-section area. We might have like a problem with a significant amount of energy lost. This was 56 centimeters squared. And it's 11 kilometers long. So generally, if we're just dealing with wires in a lab, we don't care about the resistance of the wires themselves. But, if you're driving to school and you look at the power lines on the road, they go for miles. We can have significant energy loss there. And there's actually a way to deal with that, which we'll talk about significantly later. One more thing we need to know, is the resistivity of steel. Oh, that's given here. That is 3 times 10 to the minus 7 ohm meters. So we want to find the resistance of this this trolley. And then maybe we'll apply a potential difference between the ends, see how much energy would be lost. So let's start by finding the resistance. It's a simple calculation, but let's do it. So we have 3 over 10 to the 7th power. The length is 11 kilometers. So I'm going to write that as 11 times 10 to the 3rd power meters. And the area is 56 centimeters squared. So let's throw in a conversion factor. And square the conversion factor as well. So let's do this. 3 times 11. That's 33. And then we have times 10. Oh, that's convenient. Times 10 to the 7. And the units are just going to be ohms. So here's centimeters squared, meters squared. There's 1 and there's 1. So we're just left with ohms. So let's just double check. 33 over 56. Yeah, and then we have 10 to the 7 on top, 10 to the 7 on bottom. So it's going to be like 0.7 or so. Let's just see. Oh, 0.59. Bit off. So that is the resistance of that rail. Not that large. Just for fun, let's apply a potential difference and see the rate that energy is being dissipated. Let's say the potential difference is 500 volts. We're going to move like a trolley. Probably want a lot of potential difference between the ends. So let's find the power lost. This is just power that is being converted into heat due to the resistance of the metal. So we have V. So power would be V squared over R. So let's see. Did I do this right? Okay, so let's plug it in. So V is 500. We have 2,500 volts squared. And then divide by a small resistor. 0.59 ohms. And a volt is an amp times an ohm. And let's see, we have a joule is equal to a coulomb volt, and an amp times a second is a coulomb. So let's see, I'm out of room to write this up separately. Let's cancel out the volts. Here's our amps, coulombs, ohms, and we have joules per second. So 2,500 divided by 0.59, this would be 4.2 kilowatts. A watt is a joule per second. So we had 4,240, just rounded off to 4.2 kilowatts. So that would be the energy just converted into heat due to the resistance. Okay, so yeah, that'll be it for this one.